person who's just going to do them all. Oh, well. Here we go. So, L'Hopital's rule. This is a great, that's pronounced L'Hopital, not La Hospital, or L'Hopital. Okay. So this is a French mathematician, and this idea was created not too long after the calculus was invented, or the basic ideas of the calculus within a generation, almost two away. So it's actually really intuitive. You think, oh, yeah, that makes a lot of sense. It goes like this. It's really a limit concept, and you might think, well, why don't you learn it in the first starting point when you do all your other limits, and you'll see why. So, the idea really banks on end behavior. If I asked you, what's the limit as x goes to infinity of e to the x over x, what is it? Anybody have an answer? Shout it out. E to the x over x. As x gets infinitely large, that quotient will go to infinity. Did somebody said infinity? At least somebody has a clue what I'm talking about. Infinity, okay? Now, somebody that didn't really know any calculus might say, I think it's 1. Because if you direct substitute, you get infinitely large over infinitely large. And that's infinity over infinity, and those cancel. And that's 1, right? So my question is infinity a number that you can do that with? Is infinity like 2 over 2, or hey, that's 1? Or is infinity over infinity more like love over democracy? Okay, what does that reduce to? The question is, the answer is, what does that mean? It doesn't mean anything. That's exactly what you're trying. When you try and pretend like infinity is a number and say, oh, it's this, well, then you're really oversimplifying infinity. Infinity is a concept. It's not a number. It's more like trying to reduce love over democracy. That's just weird. You wouldn't do that. Okay? So the idea then is, how did you get the answer? Now, I assume you got your answer because, actually, you tell me. How did you get your answer? Why do you say it's infinity? Why not 2 or 0? Bigger. What do you mean bigger? They're both infinitely large. More powerful, okay? I'm still looking for one different word. They both get big. Gets bigger, faster. That's the word I'm looking for. Faster. E gets bigger, faster. Now, faster is the key. I put a table off here to the side just to prove to you or remind you how powerful exponential is. Okay, they're both getting big. You can see that E is getting bigger and X is getting bigger. But even when you just get to 1,000, E is already 1.7 times 10 to the 434th power. And X is a measly little 1,000. So the quotient would already there be 1.7 times 10 to the 431st power. That's definitely stinking large. Do you agree? All right, now back to your question. When you say e to the x gets bigger faster, that was a great thing to say. And I'm going to actually quote that. It was such a great thing to say. E to the x gets bigger faster. That implies the rate of change matters for each. E has a greater rate of change, so it won. Now, if we want to consider rate of change, then we should consider what? What controls rates of change? Derivatives. And how they compare. Now this holds true for not only infinitely large and infinitely large, but also tiny, 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 and tiny, tiny, tiny. Now this is the heart of L'Hopital's rule. If you get a limit, that's always about, general L'Hopital cases are the limit of a quotient. Okay? If you get a limit problem of a quotient or a function over a function, and you get tiny, tiny, tiny over tiny, 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 0 over 0, which is indeterminate, or infinitely large over infinitely large, positive or negative, then that is indeterminate, or it kind of matters which one gets bigger faster, or which one gets smaller faster. in which case this is L'Hopital's rule. If that's the case, sorry, my notes are all over the place. This is actually how it's written in text, but it doesn't flow well. If that's the case, then the original limit can be found by taking the limit of the derivatives. Now you'll find that once you take the derivatives, everything kind of gets cleared up, and that 0 over 0 problem goes away, and you'll get an answer just by comparing the rates of change. All right, now the point I want to make sure you understand is you are to only use L'Hopital if you get 0 over 0 or infinity over infinity. Otherwise, using derivatives could lead to the wrong answer. It's only we use this in a case where we don't know what the answer is normally. Wrong answer. All right, so then, the first thing you really have to do is prove or show that yes, this is a L'Hopital case, and it's okay for me to look at their derivatives as a method. So the first goal is to determine whether it's indeterminate or not. All right. So here's the thing. This is gonna involve a little more writing than students generally like, and that's because AP especially has really cracked down on the way students were doing this problem, and it just was, a math person would read this and go, blah, because that's just democracy over love. That's gross, those don't mean anything. They don't want to see that on your paper. Don't write this. Okay? Furthermore, if you were to write this, like that again will be blah, puke. Okay? You will lose points on the AP test. And most that was actually started because professors, sometimes they have professors also on the AP grading tab just to verify that it's on a college level. And professors especially say, and this is just terrible, that's not how you do appropriate work. All right, so do not write that. Instead, the appropriate way is to say, just like in the theorem, if each function separately, when you do their limit, goes to 0 or infinity, then it's a L'Hopital case. So this is what I would like to see. Good work. Should be something like this. The limit as x goes to 0 of the top function, x cubed minus x, is 0. The limit as x goes to 0 of the bottom function, the sine of x, is 0. That's an indeterminate form, so L'Hopital would be okay to use. You really shouldn't go throwing derivatives around unless you verify, yes, this is a L'Hopital case, and therefore it's appropriate to do it. If, however, you had a problem like this, the limit as x goes to infinity of cosine of x. Now, what is the limit as x goes to infinity of cosine of x? It does not exist because it oscillates. But can we agree that it's limited to the -1 to 1 range? Yes. What about the limit as x goes to infinity of x squared plus 2? What is the denominator approach, or happens to the denominator? Infinity, it goes without bound. Okay. In that case, then, is that a I don't know, it kind of depends, or is that a yeah, I know the limit? Well, you should be able to tell me the limit. You're talking limited numbers divided by infinitely large. That approaches 0. In that case, then, you wouldn't use L'Hopital, you wouldn't use derivatives. First of all, it might lead you to the wrong answer. Second of all, it's more work than necessary. You don't use L'Hopital on I know cases. You use L'Hopital on I don't know cases, all right? So in each of these, you're supposed to show either yes, it's an indeterminate form, so L'Hopital is okay, or no, it's not an indeterminate form. It has an answer. Here's the answer. That's what I want you to do for those 5, please. How we doing? Okay. So, for the first one, did you get that it was not indeterminate? It was 0. Okay. For the second one, did you get that each part did go to 0, so it is a L'Hopital case, it's indeterminate? Yes? Same with the third one, both quantities went to 0, so it is a L'Hopital case. And the fourth one, infinity over pi over 2, which is not indeterminate, just gets infinitely large. And last, infinitely large over infinitely large is indeterminate. We would have to look at who grows faster. Are we good so far? Okay, now, that's how to decide, should I use L'Hopital? Now let's talk about using L'Hopital. Go to the fact. That sine of x over x, that's actually a famous limit that you've done at least 7 times in your math career. What is it? It is 1. Now, you first did that by table back in the day, probably in Miss Ken's class, and then we've done that a few times, and that's usually memorized for any calculus student worth their salt. Should know that's 1. You could use L'Hopital to prove it. Yes, they both get small. Which gets smaller faster, or do they get small at a comparable rate? So here we go. First, you would justify why it would be okay to use L'Hopital. The top function goes to 0. The bottom function goes to 0. Therefore, you would say, so here's where the work will start to differ. So by L'Hopital, the limit as x goes to 0 of sine of x over x can be determined by comparing their growth rates, or how they behave as x gets closer and closer to 0, which is to say we can compare their derivatives instead. The original limit is equal to the limit of their derivatives, cosine of x over 1. Well, in that case, then the derivatives would apply or approach 0 at a equal rate, and therefore the limit is 0. You with me? All right. So let's say we look at another one. The first thing I'd do is kind of mentally say, is this L'Hopital case? And I feel like the top would go to infinity, the bottom would go to infinity. So I feel like it is a L'Hopital case. Let's actually pause here. Go back here. Sorry. There's always one common mistake that people make, and I want to nip it in the bud as quickly as I can. Do you agree that we're comparing the derivatives to get the limit? Yes? Okay, now let's be clear. I understand it's a quotient problem, but I want to know what is the derivative or the rate of change of that compared to the rate of change of that. So I want to compare their individual derivatives. I don't want to just take the derivative of that. So it's the derivative of the top and the derivative of the bottom, not the quotient rule. Okay, every year I get a, we do L'Hopital, and people start saying, oh, so I do L'Hopital? Yeah, but that doesn't mean you use the quotient rule. It means compare the rates of change. So it's not a quotient rule question. Understood? Okay, so this, what is the limit as x goes to infinity? What is natural log approach? Infinity. The limit as x goes to infinity of square root of x. Now that's not 1 over square root of x. What is the denominator? As if it were its own function, what would it do? It also goes to infinity. So the top gets large, the bottom gets large. We want to know who wins. Who wins is determined by their rates of change. So by L'Hopital, we would say the original limit of log of x over root x is equivalent to the derivative ratio. What's the derivative of log of x? 1 over x, derivative of square root of x, 1 over 2 root x. I'm going to do a little bit of cleanup on that before I do the limit. The limit as x goes to infinity of 2 root x over x. Now, Technically, that's still indeterminate, but the good thing is we can simplify this. How does it simplify? 2 over root x. If I simplify it, then it's not an indeterminate form. What happens as x gets infinitely large? It goes to 0. What does that imply about the rates of change? Which one must have grown faster, the root or the log? Yeah, the root grows faster, and that's actually a really useful thing in Calc 2. Is log and square root have almost identical shapes and very similar rates of change, but the root is a little more powerful. All right. Try those 4 on your own. Showing good quality work. Individual limits shown. I know it's tempting to write that 0 to 0 infinity over infinity, but it's like multiple, right? It's just a thing that shall not be named. How are we doing? I hope you saw that one of those was a bit of a monkey wrench in the works, and the third one is it a little bit tall case? Not a little bit tall case. So you should not use L'Hopital. You should not be doing any derivatives. You should just be taking large negative divided by a small positive and telling me what the answer is. How we doing? Another minute or done with all four? Another minute, okay. Okay, so do you agree that the first one is a L'Hopital case, and therefore the original limit is equal to the limit of the derivative quotient, and so did you get one? Okay. Second one is also a L'Hopital case. It is indeterminate, and so by L'Hopital, the original problem is equivalent to secant squared of x over x, over 1, sorry, that should be 1, the derivative of which is 1, yes? Okay, the third one, the top goes to negative infinity, the bottom goes to 0. In terms of the derivative then, or the answer, a large negative is divided by a small positive. What kind of quotient do I get? Or what kind of answer? Large negative. So negative infinity. Now here's why you do all this work. If you don't get into, yes, L'Hopital is okay to use, if you just mindlessly plowed ahead and said, I don't know, I got a quotient and I got some infinities and 0, whatever, here I go. Okay? If you do that, then that's what the derivative ratio is. What does that limit go to? That goes to positive. You will get the wrong answer if you just mindlessly plow ahead with L'Hopital, throw derivatives when it's not appropriate to do so. Okay? So only use it when it's appropriate to do so. This one is a L'Hopital case. The derivative of inverse sine of 2x, did you do okay there? Do you agree with, you shouldn't agree with that because it's wrong. The derivative should be 2 over the square root of 1 minus 4x squared. Yes? Over 1. And as x goes to 0, that approaches 2. How'd that go? All right. Now, if you think, gosh, it's so much writing, you ain't seen nothing yet. Here, watch this. Sometimes using L'Hopital gets you a new problem, and that new problem is also indeterminate, in which case you do it again. And sometimes that's indeterminate, and then you do it again until you finally get somewhere. Oh, it's awesome. So here we go. This then, just on top, do you feel like it is going to be an indeterminate form? What does the top go to? 0. And the bottom, does it go to 0? It does. And so let's show good L'Hopital work. The limit as x goes to 0 of sine of x minus x cosine of x over x minus sine of x. Oh, shucks, I did them together. What have I done now? The numerator goes, look at that. How's it doing? Oh, I must have hit circle. Oh. Fun. All right. Do you agree that's 0? And the numerator? 0. So by L'Hopital's rule, the limit as x goes to 0, the original function is equivalent to the limit as x goes to 0 of the derivative. What's the numerator go to? What's the derivative of the numerator? Cosine of x minus cosine of x plus x sine of x, yeah? Do you agree? If we get a distributed negative, but a cosine's negative, derivative is positive. We? Yes or no? I might have made a mistake. Okay, the numerator is done. The denominator, 1 minus cosine of x. Well, thankfully these subtract away. That's cool. Nothing simplifies or divides out to make it better, so I guess I'll go with the top goes to 0, and the bottom goes to Ah, darn it, also 0. So here we go with another L'Hopital work. The limit as x goes to 0 of x sine of x goes to 0. The limit as x goes to 0 of 1 minus cosine of x goes to 0. Now, here's where we're going to just kind of continue on. So by L'Hopital, that thing I left off with will be equivalent to a new, an improved limit of what? X cosine of x plus sine of x over sine of x. The top, where does it go to? 0. Where does the bottom go to? 0. I guess we could break it up and get separate fractions, but we'd still have x over sine of x, so it'd still be indeterminate even if we split it. So it's still L'Hopital. The limit as x goes to 0 of it's fun. X cosine of x is 0. The limit as x goes to 0 of sine of x is 0. Don't worry, it's all good. We're almost halfway done. Just kidding, we're almost done. All right, so by L'Hopital again, one more time. The limit as x goes to 0 of, where's the numerator? Negative x sine of x plus cosine of x plus cosine of x. That's good. Now those aren't getting 0. Over cosine of x. Yay! What does the numerator go to? 2. What does the denominator go to? 1. Yay! The limit is 2. So, sometimes you have to do it more than once. In that case, we had to do it 3 times. All right. I said then I gave them 3 problems, and they said, no, we're good. So, if that's fine with you, if you want to try one on your own, or no, let's call it good. Good? Okay. So be it. Let's try an AP style one, and then we'll do it. This one's very common in the last 2, 3 AP exams. It's not like you'd see this in real life, but the idea of trying to combine several skills into one, that is a skill you do in real life, so synthesis. So that's what the AP very much makes good problems of, is synthesizing ideas, several ideas into one problem. In this case, then, they give you g as an integral defined function, which you've done a million of, but not like this. They ask, what's the limit as x goes to 3 from the negative side of g of x over x squared minus 9. Well, what about that top limit? Let's get at it. The limit as x goes to 3 of g of x. That's like or approaches that. What would the limit as x goes to 3 of the integral of 0 to 3 of f approach? 0. That's a net area question. Positive and negative areas are negating each other, so this does go to 0. What about the denominator? That's a little more analytical. That also goes to 0. So by L'Hopital, the limit as x goes to 3 below of g of x over x squared minus 9 is equivalent to the limit as x goes to 3 from below of what? G prime over 2x. Now g prime is not explicitly given, so here's where we have to take that step to communicate what about how that relates to f. So what is the relationship of g prime to f? G prime is equivalent to g is the antiderivative, and g prime is the derivative of the antiderivative, or just f, yeah? All right. As x goes to 3, what does f of x approach? Negative 3. And as x goes to 3, what does 2x approach? 6. And so our answer is? Does that make sense? Okay. All right, that's that. Questions on set 78? I had a mistake on my key on number 22, I believe. I had a wrong negative or some kind of sign issue. Set 78, number 22. There was some kind of error in my key. Negative somewhere. I can't remember what they said. There's some kind of straight negative. Oh, did I get the whole thing? I failed. Okay, questions on 78. They asked about number 1. 1 and 22? 1, 22, 15, 17, 1, 22, 15, 17. 1, 22, 15, 17. Check. Okay, number 1. Here we go. Number 1 is a cost / volume problem of a box construction. They told you that this thing had a square base, and I called those X. It had unknown height, which I called Y. And they said the cost of the top material is $240 per square meter, and the bottom also. And the cost of the sides is $1.50 per square meter. And they wanted you to they wanted you to maximize the volume you could make. The cost was capped at $360. So, given the constraints of it has to stay less than $360, what's the best way to configure this so it maximizes the volume? Feels like because the top and the bottom are so expensive, they would probably go bigger sides and less space, but I don't know. Let's see. All right. Now, first be very clear in your head what you're trying to maximize. It's not the cost here, it's the volume. What's the volume of that prism? X squared Y. Okay, now, I don't want to maximize unless I can get it down to 2 variables. So now let's substitute. The other fact is this cost. The cost, which is, I'm going to use all of that $360 we can. Let's talk about the cost of the top. Give me an expression for the total cost of the top. It's $2.40 per square meter, but then you'd have to do what? Multiply that by how many square meters? So what's the expression for the cost of the top? 2.4x squared. $2.40 per square meter times the square meters of the top. The cost of the bottom is the same, $2.40 per square meter, and you could definitely put those together into one expression, no problem. Then what about the cost of the sides? It's $1.50 per square meter. How many square meters for the sides? Each side, then all sides. X, Y, and times 4, right? So if I were to solve this for, probably solve this for Y, right, because there's so many X's going on there, that if I were to solve this for Y, I think I'd do 360 minus 4.8x squared divided by 1.5 times 4 is 6, and an X. Considering that we're going to then substitute that in, before I do that, I think I'd clean this up and split it. Call this 60 over x, or 60x to the negative first. 4.5 over 6, that's like 48 over 60, or 4/5, so 0.8. 0.8 x squared over x is x. So that, to me, is a really clean version of y that would be easier to sub in to the volume equation. Now your volume is that, and you can find where v prime goes positive to me. That was the hardest part, I felt, was the before the calculus part. Shall I, are you leaving? Shall I continue? Does anybody want me to continue with any other questions? I'll be happy to keep working. 17? Sure. 17. 17, it's not replaced, is it? Is it no, it's not. Okay. So after
Lily Holly and Lily Ingram to the second office. Lily Holly and Lily Ingram to the second office.
Nope, that's tonight's one. Sorry. Thank you for stopping here before I did this. Oh, okay. This is very much a vocabulary. Okay. So first of all, do you agree inverse mean switch? And so if I were to do that, some people would use Y here. I would use actually F inverse and F inverse. And the minute you switch, that is the inverse. Now the other thing is, when they say implicitly, that implies you don't have to solve. Yeah, so as far as, yeah, there it is. Implicitly just means mixed up, you don't solve. Okay? No, I don't mind. 22. Excuse me. 22. Okay, so F. Let's see, primer.
Lily North or Lily Holton to the financial office. Lily North and Lily Holton to the financial office.
Yeah, we can. Okay, so F double and the line tangent to F at -1, 0 as slope -6. Oh, I had a mistake. Did I tell you that? Okay. All right. So find F. So let's start with the second derivative. If the second derivative is 12x squared minus 10, then I can at least get to the first derivative by integrating both sides, yeah? So F prime is 6x, no, 4x cubed minus 10x plus c. Do you agree with that? Okay. This is the initial condition that you can use to find that c. If the curve has a tangent at -1, 0, the slope -6, then that means f prime at -1 equals -6. So that, if I were to put that in there, f prime is -6 when x is -1. That tells me then that C is -12. I made a mistake in my key. I could have sworn that's what I had.
Alex Watson,
Alright, so anyway,
please report to the main office.
I got
Alex
it.
Watson,
So then, yeah, you use this
please
to find
report
a new,
to the main office.
use to find
In
your
counseling
sequence.
today, there's a common application workshop. So seniors, come to counseling.
Okie dokie, I think I did. I don't know if I missed that one.